In this video we're going to talk about radians and degrees. Now let's say for example we were to create a function, say sin x. Now we said that the sin x is going to repeat every 360 degrees. But if you look at this image here, you can see here that this function actually repeats round about 6.28. Now if you click on here, you'll see it actually repeats at every 2 pi. Now if I was to change the scale in this axis from radians, which is in just now, to degrees, so we'll do that just now, we can change that to degrees. Now it's going to repeat every 360 degrees. So you can see the repetition is going to cut up here somewhere, 360 degrees, and this is a function that we're now looking at. It's height 1 and it goes all the way along at 360. Now this is not the main reason for using radians rather than degrees, but it's certainly something that we can think about, and that is that it's much easier to deal with the images and the pictures and representations of our basic trigonometric functions whenever we deal with a scale of radians rather than degrees. So that's us back into radians, and it repeats every 6.28. So the radians is just going to change the scale on this x-axis. Now there are other reasons and more important reasons for using radians other than this. So let's go ahead and we'll see why it is that we use radians rather than degrees. So what's the main reason for using radians rather than degrees? Well, let's look at this little example here. We know that pi is the ratio of the circumference of a circle to its diameter. So we can say then that the circumference of a circle is going to be given by pi times the diameter. And if we, rather than use the diameter, we use the radius. So the radius is going to be 2 diameters. So we can say that circumference is going to equal 2 times pi times r. So this is the usual equation we see for the circumference of a circle. Now let's say we wanted to work out the arc length of 1 degree. So what we're looking for here is 1 degree. So we've got a little drawn here, and let's imagine that as 1 degree of rotation. Then we're interested in finding this length here. So in effect what we're doing is we're going from a measurement of angle, which is 1 degree, to a measurement of length. And this length here may be, for example, in meters. So we know that 1 degree is going to be 1/360th of the circumference. So what we do is we take the circumference, which is given by 2 pi r, and we're going to have to divide it by 360, and that will give us the arc length of 1 degree. Now if we were to do that for any random angle, theta degrees, then we're going to have theta upon 360 times this circumference. So let's look at the example below. Let's say r is equal to 10, and the angle of theta we're interested in is 34 degrees. And we're asking, in that instance then, what would be the value for the arc length, and we'll call the arc length L. So again, we're just going to use the equation above. We're going to say that the arc length is going to be equal to the circumference, which is 2 pi r, times the ratio of theta divided by our 360. So that's this equation here. So we can divide out the value of 2 and 360, and it'll just leave us with 180 on the bottom. And we've still got our pi r and our angle theta in degrees. Now let's rewrite it here, and we can say that the length L is going to equal pi upon 80 times r theta. And we can put our values in here for our r, which is 10, and we can put our value for our theta, which is 34, and we can multiply that out and we get the value of 5.93. But the important point here is that we have a way of relating angle which is theta in degrees, to length. And it's related via this little equation. L is equal to r theta. So the length of the arc is equal to the radius of the circle times the angle of theta. But we'll note here that it isn't exactly equal to that. There's a scaling factor here, and the scaling factor is pi upon 180. So if we are dealing with degrees, then we're always going to have this scaling factor of pi upon 180. Now we can work it out the other way. Rather than having the angle theta and looking for the arc length L, we can have the arc length L and we can find the value over theta. So again, we can then say that our theta would equal L upon R. So all we're doing is just transposing this equation, L equals R theta, and it gets transposed to theta equals L upon R. But again, we've got this scaling factor, but the scaling factor this time is 180 upon pi as opposed to pi upon 180. But that doesn't matter. The fact is that anytime we are dealing with degrees, we're always going to run up against this extra scaling factor. Now we can get rid of this scaling factor if we work in radians. So let's see that on the next page. So in order to get rid of the scaling factor that is always present whenever we're dealing with degrees, what we can do is we can come up with a new scale for our angle. Now previously we looked at the angle in terms of degrees, and we said that 1 degree is 1/360th of the circumference of the circle. But we don't need to use that scale. We can use whatever scale we want. Now let's say, for example, we used the scale such that the value of 1, in this case we'll call it 1 radian, is equal to the angle that is generated whenever the radius is equal in length to the arc length. So if we define the angle in terms of radians, then we get rid of the scaling factors of 180 upon pi or pi upon 180, and we're just left with the equation L is equal to r theta. So to convince yourself of that, let's just consider a simple example. Let's say that the radius is equal to a value of 1. So if the radius is equal to a value of 1, we said that we've picked this angle such that the radius is going to equal the arc length. So the arc length here must also be a value of 1. So we've got L is equal to 1 and R is equal to 1, and that happens at that special angle theta, which is in radians. So we can say that in this instance here, if we were at this special angle here for the 1 radian, then we can say that the length of the arc is simply equal to 1 times the angle of theta in radians. Now you could put in other values. Let's say the length of the radius is a value now of 2. Then we can say that the length here of the arc is going to equal the radius, which again would be 2 times this angle of theta. So you can see here that in order to get rid of the scaling factor and relate angle directly to length, then we can use radians to do that. Now let's look at this in terms of the mathematics. Let's say, for instance, we had an angle of 1 radian. So 1 radian is the angle which is subtended by an arc, which is equal in length to the radius. So the length of the arc here is equal to the radius. Now let's pick a value for that, and for simplicity here we're going to choose a value of 1. So that means that the radius is a length 1 and the arc length is a length 1, and that's going to generate this angle here, which is 1 radian. That's by our own definition. So that means that if we had a circle of radius 1, then we can say that the circumference of that circle is going to equal 2 pi times the radius, which is equal to 2 pi times 1, which is just equal to 2 pi. Now pi is approximately 3.14, so that's going to be 2 times 3.14, which is 6.28. So it means that there's going to be 6.28 of these radians in 360 degrees. So you're going to have one of them here, and then 2, 3, 4, 5, 6.28 of these radians in 360 degrees. So we can say that 2 pi radians is equal to 360 degrees. Or equivalently, we could just divide out here and we could say that pi radians is equal to 180 degrees. Now, if we note the equations down below here, we had the relationship between the angle theta in degrees and the length of the arc, and also the angle between the length of the arc and theta in degrees, and we had this pi upon 180. But now if we were to change the scale of the angle to radians, then we can say pi radians is equal to 180 degrees. So if you look down here, in this instance here, then if this is changed to radians, then pi here would become 180. So that would become 180. And you can see that line there would cancel with that line, and you would just be left with L is equal to r theta. And the same thing here, pi would be equivalent to 180. We would have 180 by over 180, that would cancel, and you would just be left with theta is equal to L upon r. But we're no longer in degrees now, we're in radians. So let's summarise what we've done here on the final page. So let's summarise what we've learned in this video about radians. We said that we have a new scale for the angle, and we said that the new scale is 1 radian is equal to the angle subtended by an arc, which is equal in length to the radius. So the arc here is equal in length to the radius, and it's going to generate 1 radian. We also said that 2 pi radians is equal to 360 degrees, or equivalently pi radians is equal to 180 degrees. So this is the one we want to remember here. Pi radians is equal to 180 degrees. Now we also want to know how to convert from degrees to radians and also radians to degrees. Now we can see how to do that from the equations here. Now remember from the previous page that these equations related the angle theta in degrees to the arc length, or equivalently the arc length to the angle theta in degrees, and we noted we're always going to have this scaling factor of either pi upon 180 or 180 upon pi. Now if we wanted to go from degrees to radians, then we can say down here that in this instance here we have theta in degrees here. If we wanted this to be theta in radians, so if we put theta again, now if it's not got the little degree sign, we assume that means radians. So in order to get that here into theta in radians, we've got to get rid of this 180 upon pi. So we get rid of that by multiplying this by pi upon 180. So we're going to have our 180 upon our pi, and we're going to have our L upon our r. So in order to get it into radians, we've got to get rid of this. So we get rid of this by multiplying by pi and dividing by 180. So in that case then, these would cancel out, these would cancel out, and we'd just be left with theta is equal to L upon R. So that's what I've done up here. We've taken the degrees here and we've multiplied it by pi divided by 180. So to go from degrees to radians, you multiply by pi upon 180. Now to go the other way round about, if you want to go from radians to degrees, then we're going to have to add in the factor of 180 upon pi. So we're going to have to multiply radians by 180 divided by pi. So let's go ahead and we'll look at some of this in the simulator, and on the next video we'll just go through a few examples to ensure you understand how this is working. This simulation file is available to you in the resources section, so you can go ahead and open it up and have a little play with it. Now what we have here is a circle, and the circle is actually broken into individual degree elements. So we're going to have 360 degrees all the way around this circle. So from this point to that point is 1 degree, and then it's 2 degrees, 3 degrees, and all the way around the circle until we get to this point here, which will be 359 degrees, and then up to 360 degrees. Now what we're going to do is we're going to rotate a phasor round about this circle, and we're going to compare the value of our degrees to our radians. So I'll press play on this just now and we can watch this work its way round. So it's a little pink line here, and you can see it's counting its way round, and that's, you can see the degrees and the radian values. Now if I get up to this blue line here and I press pause, we'll see that at this blue line here we're going to have 1 radian. So that is going to sit right over the top of that blue line whenever we've got a value of 1 radian. So 1 radian then is equivalent to 57.29578 degrees, or approximately it's equivalent to 57.3 degrees. So that's another thing to note. 1 radian is equal to 57.3 degrees. Now it's going to travel round to the next blue line, which will be a value of 2 radians, and then it will be 3 radians, 4 radians, 5 radians, 6 radians, and then the bit that's left over is the 0.28, so that's 6.28 radians. So it's going to be 2 pi radians, which is 6.28 radians, is going to equal our 360 degrees. So I'll press play on this, and you can see that it's just going to continue working round about until eventually the radian value is going to go up to 6.28, which is 2 pi, and the degrees value will go up to 360 degrees. Now I suggest that you open this up and have a little play with it and ensure that you understand the scales for radian and the scales for degrees. So I'll let that just run out to the end, and you can see it's gone up to 6.28 degrees, and it actually just goes back and it works its way back again. So we'll go up to the end there, and you can see that 6.28 degrees is actually equivalent to 360 degrees. So why use radians? Well, we've got 3 reasons here in this video. One is it gives us a better scale in order to represent the basic trigonometric functions graphically. Secondly, it directly relates angle and length without any problem with scaling factors, for example 180 upon pi or pi upon 180. Now finally, in mathematics, in particular if we look at calculus, it works under the assumption that you're actually using radians. If you weren't using radians and you were using degrees, then you would have the factor of 180 upon pi or pi upon 180 within all of your calculations. So it's much easier, much simpler, and much more elegant to always work in radians. So that's all for this video. I think we've covered radians in quite a lot of detail. In the next video we'll go on and we'll look at a few examples. So thank you for listening. I'll get you on the next video. Goodbye.